Hi, welcome back. In my last couple of videos we looked at some properties of simple harmonic motion. Particularly we looked at this part. We derived the formula for the acceleration in a system undergoing simple harmonic motion. We derived that from the basic x equals amplitude. I used cos omega t, but it's interchangeable with sine omega t. It just depends where your starting point is, or you could put a phase shift in there. If you differentiate that, you end up with velocity in terms of time, and we also derived this equation, which is the velocity at any position. Okay, it's a function of angular velocity. X naught, Cambridge uses x sub 0 for amplitude. I used A in my videos. We also looked at that, we derived it. So we derived this one, we derived this one from these two. Okay. Then we also looked at the total energy in a system, and we also derived this little equation. Okay. Okay, for this video I want to look at damping. Okay, damping in particular. Understand that a resistive force acting on an oscillating system causes damping. We'll discuss that a little bit, and then we'll look at, let's get this a bit, look at the terms light, critical and heavy damping, and I'll show you some graphs that we can sketch. We have to sketch displacement time graphs to illustrate these types of damping. So that's what I want to focus on this video. And to do that, I want to use this graph. Now, this is displacement against time, and I can see in this example there's no damping, there's no resistive force, there's no forces opposing the direction of motion. The amplitude is not reducing. So this is like an ideal simple harmonic motion system. It just keeps oscillating at the same amplitude forever. Okay, but as you know, in the real world, if you ever put a mass on a spring, or you see a kid on a swing at the park, eventually the swing comes to a rest at the equilibrium position. The kid does not swing forever without putting an external force into it. So that's not really a true condition. What really happens is this. This is called light damping. Now the system will oscillate, but eventually the amplitudes decrease on each swing, and eventually it will stop. Okay, over a certain number of cycles it'll actually stop. That's known as light damping. The next kind of damping I want to use is heavy damping. So you can see it starts at the same amplitude, but this time it doesn't even reach the equilibrium position. I apply a force and I just stop it. I'm opposing it the whole time, and I just force it to stop at the equilibrium position. Okay, so this is heavy damping. That's applying a force right from the start, and I'm not even allowing it to come back to the equilibrium until it stops. Alright, heavy damping. And the last kind of damping I want to look at is called critical damping. This is where I allow it to just fall naturally to its equilibrium position, and then I apply a big opposing force. I get a little bit of overshoot, and it just sits right in its equilibrium position quite quickly. So that's called critical damping. So again, the three types of damping are on there. The blue one is heavy damping, the green one is light damping, and the yellow one is critical damping. Okay. Where would damping be used? Well, I already give you an example of a kid on a swing that's undergoing light damping, and that's just the friction in the pivot, you know, the point where the chains are connected to the bar. there's a lot of friction there, and that just causes natural light damping. Now, if the kid was in the swing and I just brought him down myself to the equilibrium position, that would be heavy damping. But if you think about where critical damping is used, if you think of something like the suspension on your motorbike, we don't want that light damping because we'd be bouncing around on the motorbike, on the road, like crazy. So what we have there is using maybe gas cylinders or cylinders full of oil. They're designed to provide critical damping. So if I jump over a little bump on my motorbike, I just feel a minimal sort of bounce, minimal oscillation, and it just settles back to a straight ride again, without any bouncing around. It increases the comfort. Okay, so that's that. Hopefully that gives you a good idea about the different kinds of damping and where it